Neurophos started with the premise that we need to go and shrink the optical transistor by 10,000x, which we have successfully done. Neurophos is an AI Accelerator Chip Company that's building optical computing chips that are legitimately 100 times faster and 100 times more energy efficient than state-of-the-art GPUs today. Optical computing has actually been an old technology that people have pursued since the late 1980s that we've known for decades is, on paper, orders of magnitude more energy efficient than electrons, but only on paper. When you try to go build these chips today, the equivalent of the optical transistor that you get from state-of-the-art foundries is massive on chip. It's multiple millimeters long, and so you just can't fit enough of them on chip to remotely compete with digital. We needed to shrink that optical transistor by 10,000x. And now we can make massive arrays of effectively optical transistors. We shrunk it so much that not only are we 10,000 times smaller than state-of-the-art optical transistors, but we're 100 times higher compute density and higher energy efficiency than anything you can get at any advanced CMOS technology node. So now we're on a roadmap to deliver a product in just a couple of years, 2028 timeframe, that is legitimately 100 times faster and 100 times more energy efficient than anything you can get in the market today.
Silicon photonics design is half photonics and half electrical. It's traditionally been done with a tool set that is more limited compared to what we use for electrical IC design. The layouts have been constrained to just simple structures because the layout tool is simple and the lack of verification. The high-speed electrical analysis has been limited to small signal response and only covering small pieces at a time. And little to no analysis has been done for things like IR drop in the wiring. As we push the performance of silicon photonics to new levels, these limitations of the tools become more severe. The difficulties of doing layout have grown with modern PIC processing. And the simple silicon photonics components of the past are running out of steam for performance improvements and for keeping up with the reduced supply voltages required by the newer process nodes. Cadence makes available a tool set that can broaden how we build silicon photonics devices. With Virtuoso, one can lay out and verify more complex components, and one can handle the slotting and fill that is needed. With EMX, one can model large areas of the layout and with many ports to represent the distributed nature of the lines and the common mode response. With Spectre RF, one can simulate both the small signal and the large signal responses, and one can trace the nonlinear components during design to optimize the linearity. With Quantus, one can extract and optimize the power distribution network. All of these things allow one to push the performance boundaries of silicon photonics design, and with a high likelihood of first-pass success. We're looking forward to working with Cadence as we at Neurophos re-envision optical computing.